We want to find the divergence of the given vector field f. The divergence of the vector field f with components p, q, r is denoted using this notation here, where we say div f equals, as a dot product we have del with the differential operator dotted with the vector field f, where this dot product is equal to the sum of these partial derivatives. So notice how the divergence of the vector field f is equal to a scalar function, where remember, when we found the curl of vector field f, the curl of vector field f was another vector field. Let's go back to our example, find the divergence of the given vector field, then we'll talk about what it means and also show it graphically. So again, if we use this formula here, we would have p equals yx to the fourth or x to the fourth y, q equals xz to the fifth, and r equals z y to the sixth or y to the sixth z. But let's show this as a dot product. So the divergence of the vector field f is equal to del dotted with the vector field f. So del, the differential operator, is angle bracket partial with respect to x, comma, partial with respect to y, comma, partial with respect to z. Dotted with the vector field f, which is here, let's write this as x to the fourth y, comma, xz to the fifth, comma, and y to the sixth z. Now determining the dot product, this would give us the partial derivative of x to the fourth y with respect to x plus the partial derivative of xz to the fifth with respect to y plus the partial derivative of y to the sixth z with respect to z. So the partial derivative of x to the fourth y with respect to x would be 4x to the third y plus the partial derivative of x z to the fifth with respect to y would be 0 plus the partial derivative of y to the sixth z with respect to z would be y to the sixth, which means the divergence of the vector field f is equal to 4x to the third y plus y to the sixth. Now let's talk about what this tells us about the vector field f, and we'll also look at this graphically. The divergence of a vector field measures the rate change inward or outward of a vector field, also called sync. For a velocity vector field, this would represent the rate of flow inward or outward from a given point. If the divergence is positive, the rate of change is outward, like a heated gas that is expanding. If the divergence is negative, the rate of change is inward, like a cooled gas that is being compressed. And finally, if the divergence is 0, the change is not inward or outward, the velocity field is called incompressible. So if we consider a small balloon in a vector field, if the balloon is expanded or stretched, then the divergence is positive. If we see small pieces of balloon flying away in all directions, that's a sign of positive divergence. If the balloon is being compressed, then the divergence is negative. If we see a balloon that is shrinking, then the divergence is negative. And finally, if the balloon is being carried along without being stretched or squished, we know the divergence is 0. So going back to our example, let's find the divergence of the vector field f at the point 1, 1, 1, and then we'll look at it graphically. So the divergence of the vector field f at the point 1, 1, 1 would be equal to 4 times 1 to the third times 1 plus 1 to the sixth, which equals 5. So because the divergence is positive at the point 1, 1, 1, this tells us the rate of change at this point is going to be outward. So in gray we have the graph of the vector field f. This red point is the point 1, 1, 1, and notice how looking at this vector in the vector field, we can see how the rate of change is outward at this point, which again is the reason why the divergence is positive at this location. I hope you found this helpful.